Let's take a look at number 1 on the concepts page. We talked about the conditions necessary for simple harmonic motion, or SHM. There's really two conditions, although you may have put them together all into one statement. One of the conditions is this, that we need a restoring force that acts to bring the system back towards an equilibrium position. It's okay if you didn't write it down exactly like this, but as long as you have something in your answer that refers to a restoring force. The second condition is that the driving force has to be proportional to the system's position away from equilibrium. This is all typified really in just one equation, Hooke's law, F sub s equals negative kx. So clearly the spring force is proportional to x, the position away from equilibrium, and that negative sign means that whichever way the system is stretched or compressed away from equilibrium, the spring force acts in the opposite direction. You stretch the spring out, the spring force tries to pull it back in. You compress the spring in, the spring force tries to push it back out to its natural position, its equilibrium position. And so basically, a mass on a spring is a perfect example of simple harmonic motion, and any system driven by a force that follows Hooke's law fits the bill of simple harmonic motion. There is another way to express this, because if we're considering, for example, mass on a spring, maybe a horizontally mounted spring on a frictionless surface, the spring force would be the net force acting on the object attached to the spring, in which case sigma F equals ma. We're going to replace the spring force with ma, so ma equals negative kx, and then solving this for a equals negative k over m times x. This is another way to express it, either that the driving force is proportional to the system's position away from equilibrium, or the acceleration is proportional to this position, and the acceleration also has to point opposite to the position. So this last equation is another statement of the condition necessary for simple harmonic motion. Again, a mass on a spring is a perfect example of a simple harmonic motion system set into oscillatory motion. But let's look at another example, specifically the pendulum. Let's look at specifically a simple pendulum, just a mass on a string swinging back and forth in a straight line. X equals 0 is the equilibrium position. That's where it would be 0 degrees away from the vertical. So let's say it's out some angle theta away from equilibrium, and it's moving back and forth, oscillating back and forth. Let's say at this particular moment in our picture, it's moving away from equilibrium, so we'll call that the positive direction. Which way is it accelerating? Well, it's trying to accelerate back towards equilibrium. So even as it rises away from equilibrium, we know it's slowing down. So in a tangential sense, we know it has a linear acceleration pointing back towards equilibrium. Let's draw a free body diagram, of course starting with mg pointing straight down. It's a mass on a string, and so of course we know there's going to be a tension force, and the tension force points along the string. Strings only pull. Let's assume no air resistance, no friction, just an ideal situation. So there's our entire free body diagram. If we want to analyze the motion of the system, we see that there's a linear or tangential acceleration back towards equilibrium, so we obviously have to resolve some forces into components, in which case it would be mg. We can see tension is at right angles to the acceleration, so we were going to resolve the weight vector into its components. One of them points in the radial sense, away from the center of motion. The other one points tangent. Then we just have to play our usual game of find theta. It's a pretty simple game of find theta, considering theta is measured from the vertical, which means theta is just going to translate right down to there. And now we can apply our trigonometric knowledge here to say that mg sine theta is pointing back towards equilibrium, mg cosine theta is pointing away from equilibrium. If we were approaching this from a circular motion point of view, we could talk about the centripetal force and the combination of tension, mg cosine theta, but right now we're not looking at that. We're just looking at the acceleration back towards equilibrium, trying to relate this to simple harmonic motion. So we do sigma F equals ma only in that dimension. There's only mg sine theta pointing in that dimension. Notice it is in the negative direction. We're calling positive away from equilibrium, so mg sine theta points the other way. That's negative mg sine theta equals ma. And it's pretty easy to see the mass is going to cancel out, and the acceleration in the tangential sense is negative g sine theta. Now the pendulum is an oscillating object vibrating back and forth with regular periodic motion. Is this simple harmonic motion? Well, we just talked about the conditions for simple harmonic motion, that the acceleration has to be negative k over m times x. K over m is just some sort of constant, so we don't have to worry about that, but it has to be some constant times x, and it has to have that negative sign. Well, a equals negative g sine theta has the negative sign, but it's not proportional to x, the position away from equilibrium. It has to do with the sign of the angle. So this is not quite simple harmonic motion. But let's see if we can take this from a different perspective. Let's redraw the picture from sort of a geometric perspective, the actual dimensions of what's happening. So we'll call capital L the length of the string. And when the mass is in its equilibrium position, capital L is that dashed line. Theta, again, is the angle away from equilibrium. And here is x, its position away from equilibrium. I'm calling it in the positive direction, aligning it with the positive direction assigned here with V. And you should see that this is an isosceles triangle. This L is this L. And the angle, let's assume, is a relatively small angle. For this case, we get to use what's called the small angle approximation. Now, at this point, I want you to take out your calculator and put it into radian mode. And we're going to take the sine and the tangent of some very small angles. Okay, so go ahead and take, for example, the sine of 0.1, and then take the tangent of 0.1. Okay, let's make it even smaller. Take the sine of 0.01, and take the tangent of 0.01. What do you notice by the values of sine and tangent and the angle itself, as long as, of course, you are in radian mode? Well, you should be able to see that the value of the sine and the value of the tangent of the angle are very, very close to each other, and hopefully you also see they're also very close to the angle itself, as long as we're in radian mode. And this is the small angle approximation. For very small angles, as long as theta is in radians, it turns out that the sine of the angle is almost the exact same thing as the tangent of the angle, which is almost the exact same thing as the angle itself. Again, it has to be in radians to see that. All right, so why is this useful? Well, again, let's assume this angle is relatively small, and well, it's not exactly right. Let's pretend it's a right angle. Now, it's clearly not a right angle because this is an isosceles triangle, but if theta is really small, can you see that this angle here is kind of close to 90 degrees? If theta is really, really small, it's really, really close to 90 degrees. Even though we know it's not, let's just make an approximation, because this is, again, the small angle approximation. So now let's talk about the sine of theta. Well, sine of theta is opposite over hypotenuse. Opposite is x. Hypotenuse is L, and so sine of theta is x over L. In our equation here, we have sine theta. So as long as this angle is small, we can say sine theta is x over L. We can replace sine theta with x over L, and now we have A equals negative g times x over L. If we just regroup that, that's negative g over L times x, and look at that, that is simple harmonic motion. Don't worry about the fact it's a different constant. As long as the acceleration is proportional to position and points in the opposite direction away from position, well, then it's going to fit the bill for simple harmonic motion. The constant in front is just something different depending on what sort of system we're looking at. And so we can see for small angles, we can say that the pendulum is almost simple harmonic motion. It's never exactly simple harmonic motion, but it's good enough for our purposes. A mass on a spring is a perfect example of simple harmonic motion. The pendulum is for only small angles. Now here, we're talking about in terms of radians. Usually in terms of degrees, we say maybe less than 15 degrees or so would be a good number to cut it off at, where we can still apply the small angle approximation, and the equations for simple harmonic motion apply to the motion for a pendulum.